Thank you very much, Kyle, and thank you for doing this Ferro Talks for about almost coming to the year. We appreciate your effort very much. Good morning, good afternoon, good evening, colleagues, friends around the world, and thank you for being here to share some of my experience for past so many decades, this time on piezoelectric and dielectric composites. I am from Rutgers University, Department of Material Science and Engineering. Laboratory is called Glenn Howard Electroceramic Lab. So this is a historic overhead representing the huge major contribution of Professor Robert E. Noonan in the area of piezoelectric ceramic polymer composites. What he proposed on electronegativity, as well as the direction of the composite, basically, I will say that revolutionized few applications of piezoelectric materials. So here in the schematic diagram, you see the 10 different connectivity patterns or self-connectivity patterns of piezoelectric ceramic polymer composites or any dielectric or any ceramic polymer composites. And among these, which is I colored here, a few of them became very important and extensively researched, these composites connectivity patterns. And I am going to highlight in my talk. And basically, this is another historical talk on the ferroelectric or piezoelectric related area. In the composite, we look at flexibility, conformability. We look at the low density for better acoustical matching. This is the piezoelectric, as well as the connectivity pattern, whether we have a good electrical path or mechanical or stress distribution. All days, these are the coefficients we look for optimizing piezoelectric properties of particular composites. This is 50 years anniversary of the polyvinylidene difluoride. 1970, Kawai from Kyobashi Institute of Physical Research, now is in Yokohama University, developed a special polymer, which is the uniquely piezoelectric, and that's called polyvinylidene difluoride, CH2CF2N. PVDF comes in 3 different forms. It is alpha, beta, and gamma form. Beta is the most desirable one for piezoelectric application. So I listed piezoelectric properties of the PVDF, few from many articles and some from Professor Robert Noonan's book. And this was a raw model for us to develop piezoelectric composites, especially when this came, Navy very much became interested on the PVDF because of very high G coefficient, and then as well as the low density. So I will talk a little bit about early composite 331303 connectivities, then move to the fine scale fiber composites. And then I talk about a couple of overheads on different 3D printing process, working on or worked on the piezoelectric composites. And then recently, really, composite became major focal point for the many applications that includes energy storage, energy harvesting, and capacitors. And a lot of novel processing is there now making composites. First, I would like to acknowledge Professor Noonan and Professor Cross, as well as Professor Walter Schultz, and their leadership on piezoelectric composites, idea, and connectivity pattern. Walter Schultz ongoing lab with us on doing characterization, setting up all the hydrostatic measurement or piezoelectric coefficient evaluation. And also I would like to acknowledge Dr. Robert Pohanka and Dr. Wally Smith of ONR. Probably Bob Pohanka is not there anymore. And they not only supported Penn State MRL ferroelectric for many years, from composite to the single crystals, but also supported people like me and many other colleagues, not only in the US, but also in some other part of the world on development of piezoelectric ceramic, polymer composites, and single crystals. It is noticeable to acknowledge contribution of Professor Kiyoshi Okazaki from Japan. And he and Professor Cross did tremendous job organizing US-Japan dielectric and ferroelectric, which is still going on every other year. This is only by invitation. And Professor Tom Sherrod, or Tom, as we call, he made a major contribution on piezoelectric composites. And two of my very close friends and my office mate, Rajgur Raja and Arvind, each of them had excellent contribution on development of piezoelectric material. And this is the pictures from their graduation in 1984. This is the overhead Professor Newnham showed many times, all days, and putting together different connectivity patterns of different composite developed. He has really a genius idea. And he got a lot of hardworking people, and then there was many technological breakthroughs. And so these are the old composite. Later it comes munis and then symbols and so on, which I touched some of these very briefly. This is schematic drawing of many composites developed around the world. And so this is from one of my review articles. And so here is the PVDF. We call PVDF as a composite as well. And then here is 03 composite. The lower part composite you see here is developed by so-called, we said at that time, layered manufacturing or solid freeform fabrication. Now we call 3D printing. Let me just historically, for the importance of this type of composites, start with 03 composites. So after Kawai's development of PVDF polymer, then there was a couple of activities on making composite in Japan based on the PVDF. But the main point came from the Harrison from Honeywell on making PZT polymer composites. And these composites showed a decent properties, but it became really a major point for moving the piezoelectric composite research at Penn State. I remember very well Harrison, when he was a part of the industrial representative to ferroelectric at MRL. He was very well distinguished individual and knowledgeable. So from there, I am going to show a little bit busy overheads, but as historically, this is the first composite reported at Penn State. It's called replenament or replication form and replication process. And this is Doyle Skinner work. He started about maybe 76 and finished thesis on 79 or 78. But my memory says that he defended his thesis, but he never submitted his graduation. And so he stayed it like that and working in the major lab in the Columbus area. Tom Sherrod and Rittenmeyer came, another composite is called BURPS, burning plastic sphere, that is the abbreviated. Then a couple of 03 composites from Japan, porous or ladders. And then most of our reliable result came evaluation of these composites at Orlando Navy Lab by Dr. Robert Ting. He was a very nice, knowledgeable person. He evaluated most of the composite collaborating with Penn State as well as supported by ONR. So this is a typical G coefficient of 3,3 composite versus the pressure. And remember, these composites aimed to be used underwater hydrophone application, underwater navigation, or whatever you call. So looks like this gives very reasonable stability with the pressure. Cycling is great. And at the same time, Ken Killiker was working on 1,3 type composites. Idea of 1,3 type composite came from the Harrison as he used larger PZT particle in 0,3 composites. So Professor Krauss used to say that this is the hard-working graduate students. So he had a rack here, make these PZT fiber by extrusion, sometimes hipping process, and then take one by one, put in this rack, embed in the polymer, and then dice it to make 1,3 type composite. He look at low frequency hydrophone application. This is typical D33 versus volume fraction. You get D33 of about close to the bulk material at 50 volume %. Later in a year, Savvakas made simplified techniques. Savvakas was an undergraduate student, but brilliant guy, and he was doing this one as a senior project under Professor Nunam. So I wonder why they didn't patent these 1,3 dice composite at time, which is now it is the base of the medical imaging application of these composites. So it is basically taking PZT block, dicing one way, dicing another way, backfilling with the polymer or foamed polymer. Guru Raja made huge investment on characterizing high frequency application of these composites. This is example of thickness coupling coefficient versus temperature. And so stable, very thickness coupling, good thickness coefficient about maybe 70% or so, all the way with up to 150 degrees C. This is my graduate work. And so when I started doing research with Professor Nunam, which he was outstanding scientist, researcher, leader, idea maker, and as well as advisor. So he handed out the paper to me and he said, make a PZT sphere. And then from this PZT sphere, make a composite. And let's see how the property looks like. The result came very useful. We published a paper, but not that I was looking something dramatic. So I was always thinking that, okay, how can I make inverse of the PZT sphere? And so I came with these type of composite. This is the patent. I believe this is second patent for Ferroelectric Group at MRL. The first one, 1,3 composite by Killiker. And so this is called perforated. We can have this one in 1,3, 2,2, or 3,1, 3,2, 3,1, 3,2 connectivity. Less pressure sensitive, but very high DH and very high GH. And the product of DH, GH is the 15,000. This is the overhead Professor Nunam presented at the 1983 ONR review meeting of the program. And so for a time, we were proud that we have an outstanding composite. This is 9 elements packed together by Celanese Incorporated, New Jersey at that time, Morristown, New Jersey, based on these 3,2 composites. Let me go back to the, again, PZT particle polymer composites. One can put all kind of polymer listed here, depending on their electrical connectivity. And then you can put variety of filler material. BT and PZT was traditionally used, but then, you know, why not some other piezoelectric particles such as lead titanate, bismuth ferrite, and going so on, and many others. But this type of composite is not easy to polarize. You know, look at this applied electric field in the composites, and it comes the relationship between the dielectric permittivity of polymer and dielectric permittivity of the ceramic. So if you apply about maybe 100 kV for Poland, you get only a few % on the ceramic. And so this is from von Hippel, I derived this simple relation to show that the voltage applied to the ceramic depends on many variables. And then the best thing is to have a very thin polymer between the ceramic particle, as well as matching their electrical conductivity. So in 1982, Haizou Bani put a bombshell in the community. He introduced several different types of composites. And these composites are 0,3 composite made by lead titanate particle. Lead titanate, we believe that he made by chemical processing with controlled particle size, excuse me, with controlled particle size, and sometimes in the composite, he mixed different particle size. Finally, he announced a composite with DHGH in the ranging between 2,500 to even 3,000 or more. And that was really breakthrough, comparing with the old 0,3 composite of PZT polymer, or even comparing with the PVDF properties. So from that time, the majority of the effort at Penn State was on making 0,3 composite. So what you see here is list of many 0,3 composites made by different individuals with different filler material, with different powder, with different ceramic processing. So I believe the most significant is here is starting using the lead titanate bismuth ferrite. And Jenny Genevitz, late Jenny Genevitz, very young, nice lady, died early. She was a professor of University of Indiana at Pennsylvania. And so she worked on this composition. I should say that I had involvement on all these composites, either when I was at Penn State or later leading at Rutgers University. Well, the second composite, which three of us, Rajguru Raja, Arvind Halial, and myself developed during our postdoctoral research period, was PZNPT ceramic PZNPT single crystal particle on the polymer composite. And so this composite gave similar properties of single crystal. Yong Li, a visiting professor, worked co-precipitated lead titanate. Moon Lee worked on size effect on the lead titanate 0,3 composite. Kathleen Hanner, she worked on paint composite. And later, we worked at Rutgers University on lead titanate bismuth ferrite composite. And noticeably, we processed composite by colloidal processing, and we made PTBF by chemical process. And the uniformity of these composites made by chemical processing as well as colloidal processing was outstanding and gave DH of about 6,000, comparing few thousand DH of made by other particles or processing technique. So let's look at 2,2 composite. 2,2 composite, again, I said I wondered that why Penn State didn't apply patent on that one. So we got a special patent on making a 2,2 composite by lamination of the tape, and we made either 2,2 or 2,02 composites, and as well as 1,2, 1,3, 103 composites. So we utilize these composites, meters of these composites in the road, in corner of the road in the Rutgers University as a way in the motion, working with the faculties from civil engineering. And we look at it really loading and unloading response, and seems that vehicle is arriving, and we wanted to see how was the response of these composites. Composites really responded positively, a little bit delayed response, but it followed the load and unload cycle here, and the voltage sensitivity was really good at that time. And so this was a candidate replacement for fiber optic sensors for the way in the motion there. Early or late 80s, Plessey came with a composite, and this was very interesting also. The result, again, what I am showing here is from Bob Ting, and this composite was very large area, a panel. We believe that this was diced, either 1-3, probably, or 2-3, or 2-2, and so DSGH of these composites was about 20,000. For about a decade at Rutgers University, graduating about maybe 5 or 6 graduate students, we worked on fine scale fiber composite. This area became very interesting because we want to have smart piezoelectric composite touch sensor, even for keyboard. ONR supported this work as well. So first we started making this by relic process, taking a fabric, this could be a carbon fabric, cotton fabric, and then immersing in this salt gel solution of the PZT after drying, careful drying, and then we impregnated with the polymer, we made a composite. This is really fine scale, and the properties was great. And later, ONR helped us to put together a CTR proposal with the Advanced Metrics Incorporated in New Jersey, and we developed PZT fiber continuously by VSSP process. And then later, we made variety of composite based on these fibers, as well as the bimer, as you see here. And so that period was very good period on PZT fabric composite, and this resulted on mass producing of the PZT fiber, as well as making these 1-3 type composites as a bimer for either structural protection or crack investigation. So where we are now. So, we started with Ken-Clicker, and then FMI proposed at that time with the support of ONR, mass produce these composites. Later, Andreas Schoenecker from Fraunhofer made these PZT fiber by a plastic mold process and developing very fine scale, beautiful PZT fiber and incorporating in the polymer composites in different geometries. MSI, late Les Bown, my mentor as a postdoc, he was my postdoc. They came up variety of design of PZT ceramic, including 1-3 tube, and this is part of our work also, and by injection molding. So that was in terms of the composites and fiber. Then it comes polling. It was the first Rajguru Raja made continuous polling of these PZT fiber. Just taking single PZT fiber and drawing between 2 electrodes in the oil bath and pull them continuously. I looked at the picture. Picture was not clear to put it here, so I wanted to notice his work. When I was at MRL, I proposed to apply PVDF to work, to polarize composites and ceramic. Then later we came at Rutgers and we processed and optimized this corona polling process for continuous polling of composites. Very, very intelligent Nesbitt Hagwood from MIT, mechanical engineering. He proposed finger type electrode and polling them horizontally like this geometry there. So this became really a way of working really large area fiber composites. So in terms of, those are low frequency. In terms of high frequency, there is a lot of PZT and recently some other ceramic polymer composites. I am noticing few different contribution. This is from Jinfeng Li and Qiufa Zhou. Jinfeng Li from Tsinghua, Qiufa from USC. They made K&N-based material by dicing and make composites. And this is about 32 megahertz center frequency, very nice bandwidth here. It's about 70% minus 6 dB bandwidth. And then some other scientists around the world made these composites, K&N-LT, ceramic polymer composites, and BNT single crystals and BNT fiber composites, which they give really encouraging results overall for development of ceramic polymer composites. This is another work. This is single crystal made with Haizelu and his group on really lead indium niobate, lead magnesium niobate, lead titanate, single crystal 1,3 type composites. Here is the single crystal, and these are the polymer here. And the bandwidths of these composites is about 107. This is minus 60 dB bandwidth. And again, that was another encouragement, really using these for medical ultrasound application. So about 2 decades, we worked on the 3D printing at Rutgers. We had major program supported by DARPA, ONR, New Jersey Commission on Science and Technology, few industries, and we didn't call 3D printing, we called layered manufacturing, we called solid freeform fabrication, but now it is a fancy to call 3D printing, which it is in the, really, now it is printing. And so here is, if this works here, but I am not sure. So this is 3D printing. With the 3D printing, we made mold. And from these molds, we made really fine scale composites here, or making this mold. And this is a plastic mold, the reusable mold, make 1,3 composite, or make volume fraction gradient composite, concentrate major property in the center, and then go in the side of the composite, lower property. Specialty is we have a patent on this one, wagon wheel composites, and this is another outstanding composite by 3D printing. So I have 2 work here to show to you. One is an incredible composite by Michael Hahn, and this is again in the 80s. What he did, this is PZT aligned in the polling direction, that is PZT, but he incorporated glass fiber in the transverse direction, as well as possibly foamed polymer also. The purpose was eliminating D31 coefficient. So D31 in the PZT is a negative and basically kills DH. He successfully did by designing these composites and producing it. So this is a patent on late 80s to MRL. And what we did on 3D printing, we really made a shape that fiber or ladder make 45 degrees with each other. And we polarized these along the fiber, and we tried to bring contribution of D15 as well as eliminating D31 and D32. The result of this one is really a composite with 50,000 DHGH and DH about close to the 550. I believe this was outstanding design. Of course, this didn't go to the mass production yet, but there is no match for these piezoelectric composites. Here is 2 different 3D printing process. One is contribution of GE courtesy of Scott Smith. The other one is contribution of Joe Cicerano. This is the old overhead I had from Joe. Joe is the president of Robocast Enterprise. And so they made really, at that time, this process started from Sandia National Lab. Now it is a major company in Albuquerque, New Mexico. And they make variety of porous ceramic by 3D printing, robocasting. And of course, this is a patented process by GE. They make 1,3 composites, and they made a hydrophone out of that one, not hydrophone, or probe for high frequency medical ultrasound. And this is the result of that probe. So 3D printing works, and new technologies back on making piezoelectric composite. One of the major composite with Professor Nunam's made it, or idea came reality, is symbol type of composite. And this is PZT ceramic, shaped metal glued in the form of the symbol. This composite was a point of attention for many, many years, and still it is for many researchers, as well as it has a couple of mining application as a sensor, and it is a good actuator also. So we had some contribution on these composites, and this is a composite of PMNPT ceramic, piezoelectric, PMNPT ceramic relaxer with 2 metals electrode made by 3D printing. This is the showing the cross section of these composites. Bimorph, now it is being used a lot on energy harvesting and possibly on energy storing application. So I want to move to the new direction here. What is happening? This is really novel composite the group made in Korea here, and this is publication by Journal of American Ceramic Society. This is a composite of multi-layer. PZT is multi-layer here, and then the polymer shows here 2 connectivity here. So this is brilliant idea, and this composite shows D33 about 1200, and due to the design, the D31 and D32 negative, and very impressive DHGH. We took Professor Nunam's composite, symbol composite, we designed in bridge mode, in the bridge design. And then rather than having simple ceramic disc, we segmented the ceramic and polarized and connected so that it is multi-layer. It works like a multi-layer ceramic there. And this composite gives really outstanding effective D33. Effective D33 of this composite about 19,000, as well as we developed a prototype 64 element energy harvester. And here is this one of the equipment we have. We just put together a system that looks like car is driving, applying pressure in the frequency, and then looking at the voltage generated. And then, you know, this eliminates about over 10 LEDs there. So that was basically one of the recent work, last 2 ones. And this is really another outstanding process for development of highly dense composite, as well as sintering ceramic at low temperature. Last week, Professor Clive Randall was at giving virtual presentation seminar to our graduate program. And he talked about their really breakthrough on development of cold sintering process for making 95%. Say, for example is the barium titanate, and only 3% polymer, basically modifying the grain boundaries here. And schematically, we show the process in the right hand. And so here is the Here is the 2.5% polymer, then it goes to the 5%. 2.5% is a little bit lousy material, but then when it goes to the 5% or 10%, you have about 1,000 permittivity, and then the density goes about 95 to about 98%. So this is a review. There's many review articles on this one, and this is the way it's going to be making highly loaded composites, possibly by cold sintering process. Again, this is another outstanding paper from Penn State MSc department, and this is on gamma alumina composites. They look at it, not only alumina, they look at it titanium, they look at it silicon. And here is the gamma alumina is kind of anisotropic particle. It's like platelet or flake geometry, highly loaded. And the idea is here to match dielectric properties of the filler material with the dielectric properties of the polymer material. So the polymer matrix is PVDF. Now we have, here is the filler is alumina nanoparticle, alumina nanoplate, and then this is the PVDF property itself. You see that by going to the alumina nanoplate, then you can improve electric field strength as well as electric displacement quite impressively from pure PVDF to a very highly loaded gamma aluminum oxide. In the same way, discharge energy density, output, as well as current density became incredible. Current density is low, and discharge energy density and efficiency became really outstanding. Electrospinning is making a lot of noise. Electrospinning is not new or is not new. We worked on electrospinning of bismuth ferrite nanofiber, and Ruth Rivera is in the Martin Marietta now. And so by simply putting your solution, whatever nanoparticle solution is in the particular polymer here, and by applying electric field, you are just simply creating nanofiber here. You can collect nanofiber in the pattern you wish, make a organized 1,3 composites or 3,3 composites, or you can have a nanofiber particles or nanofiber mat, and then either put, here is, for example, keratin solution coming from the wood, make nanocomposites for cell voltage generation here. And this is another example of this electrospin piezoelectric composite. This is an electrospin mat here, gold electrode in the substrate, flexible substrate for self-powered energy generation for variety of application. We are talking about looking at the voice recognition. We are looking at possibly looking at the blood pressure and so on. So finally, in all those things, surface modification of the nanofiber became very important. Surface modification try to, for example, put acetic acid to increase loading. For example, put another coating having a cold shell structure. But this is probably my last overhead before making summary here. And briefly, I am talking here is flexoelectric composite. And this is Professor Krause came this idea in 80s, and he was asking who can make pyramid type composites. And so as sharper as that really concentrate static stress into the strain gradient and make a lot of polarization in the composite. This is the papers from recent publication. So here is BST composite. Here is the BST. Here is the tape casted, then putting some metal here, and by applying stress, then you generate about over 1,000 picocoulomb per Newton D33. I recall from the paper at about below TC, even numbers are very high. This is another novel design. This is thin film, really making compositional gradient. In my collection is maybe this is made by a PLD process, and every few layers you are changing the composition. So this works very fine in the macro scale to develop nano scale flexoelectric thin film, which should give outstanding properties. Major advantage of this one is no fatigue and could be used for energy harvesting as well. So there is many application for composite. As of now, major healthcare application. And you see that here is the 1,3 single crystal composites work in medical diagnosis, cardiology application. Composite could be used on homeland security, could be used in energy harvesting. We worked with New Jersey company to develop fabric composites or fiber composites for utilizing in the sport utility, including tennis racket for vibration or tennis elbow control. We have worked on these high Q composite for therapeutic transducer application. You can have energy generation, and this is a composite here. This is the probe of these used for all these cardiological ultrasound application. This probe this is the yellowish color, is diced. Now it is single crystal, used to be a ceramic. Then few different type of polymer or composite matching the air and lens, and then composite backing the air. So all the probe is the composite here, consists of many, many elements there. With that, I want to thank my group. I am going beyond my limits of presentation. I want to thank Jake, Jack, Hao Chan, and Akil for their hard work during this situation we are, and also helping me on discussion with these overheads. Thank you very much for your attention. And I wish you a happy holidays to every of you.